Okay, team, we're going to talk about the pump project. This is the third component of the water distribution system design project. And previously you designed a tank elevation. So let's look at our little system here. You've got a storage tank. You figured out the elevation of that bottom of the tank such that we supplied the appropriate pressure and flow rates to the system under various scenarios, and also the diameter of that tank. Now we need to design the pump system to deliver water from a storage reservoir through the pipes to the pump, and then again through the pipes to the tank. So take a minute to read this material. This kind of sets the project up. There's so many feet of such a diameter pipe leading up to the pump right over here, and then so much pipe leading up to the tank itself. So that's the system that we are designing under. And you'll use that information to develop the system curve, which I am showing here. So this red line is the system curve. And depending on the elevation of the tank, that's going to be the head the pump would have to supply at 0 feet, zero discharge. And then as discharge increases, obviously we have this kind of curved pump curve here. Now the pump you're using is the series B60 crown pump here. And we're using the biggest pump in this series, which is the B6012X. Here's what our pump looks like. It's a big boy. I don't know what the dimensions are here. It looks like inches. So yeah, take a look at that. It's almost not quite 3 feet, 2.5 feet, or a little bit of 2 feet in diameter. So we're talking about a big pump here. And we're going to be using either the 1750 RPM or the 2000 RPM pump curve. A lot going on here. It'd be nice if they use different colors. We have efficiency here, and so it's kind of like an efficiency surface. These are contours of efficiency. And we have the dashed lines, which are the brake horsepower that the pump is supplying. Or sorry, the energy that the pump is requiring. So the brake horsepower is the energy. So that's the dashed lines. So a lot of information here, and then of course the pump curves, net positive suction head. We're not going to do that calculation right now. So if we go under modules on Canvas, here's the PDF that we're looking at right over here. And then here is the actual values for the 1750 and 2000 RPM scenarios for this pump. So we just went to a tool that can give you the XY values of an image and kind of extrapolate those out or collect those values. So that's what those values are. They're in this CSV file. So your job is to first figure out how much flow we need, or what's the volume that we need to deliver to the storage tank, and that's going to be the maximum volume of water to pump in a single day, plus that emergency value. So that's going to be the non-fire emergency volume, that 25%, plus the volume for maximum supply or maximum day. So that's the volume this pump needs to be able to pump up. And if we look at this situation, we need to be able to pump that over 6 hours. So that's between midnight and 6 a.m. Okay, so that's going to be the hours. And then this is going to be then the flow rate that we need to deliver that volume of water over 6 hours. We've got our elevation of the tank bottom here that you figured out, elevation of the ground, storage reservoir. So what's the elevation? What's going to be the maximum water elevation difference in the storage tank relative to the reservoir? So this would be the value elevation value of the water in the storage tank right here, so delta H compared to the reservoir elevation. And of course, that would be when the storage tank is full. So we got our pipe length, the roughness, diameter, relative roughness. We'll put in some constants here, viscosity, gravity, and then we're able to generate the system curve. You might want to actually extend this table and make some more rows here to give yourself different flow rates. But we'll put different flow rates in here, calculate the velocity based on the diameter, the Reynolds number, the friction factor. You can throw in your Swami-Jain equation here. And then this will give you the required head at a given flow rate, which includes the elevation that we have to pump up, as well as the, so that'll be the maximum elevation, as well as the friction loss in the system. So that's table 9. That'll give us our system curve, which I have shown here in red. Now we're going to think about the pump curve for a single pump. So we've got our pump curve right here. This is at 1750. That might work. You might want to go up higher to 2000 RPM. And we're going to need a certain amount of pumps in series and parallel. As you can see, this pump curve is pretty far away from our system curve. So we're going to need to certainly do some pumps in series to increase the head from this pump so that we can intersect that system curve. So we have pump series and pump parallel. And for a single pump, here is the flow rate that the pump would deliver to the system, the head required for the system, and you can actually create, for a single pump, you can create a quote-unquote system curve for a single pump by simply dividing the system curve by the head values by the number of pumps in series and dividing the discharge values of this curve by the number of pumps in parallel. Okay, so that'll be your system curve for each pump. So the reason why we calculate the system curve for each pump is so that we know the efficiency at which this pump is operating. And so what for a given flow rate, we can then go back to our pump curve and we can say, okay, each individual pump is providing this such and such head and such discharge. And then we can go back and calculate the efficiency that pump's operating at. So that's the reason we do that. To actually get your system pump curve, this green line, of course, we multiply the pump curve's head values by the number of pumps in series, and we multiply the pump curve's discharge values by the number of pumps in parallel. And that's what would generate this green line. So you want to generate this green line so that it intersects the red line at a discharge rate close to what you actually need. And you don't want to go below, you want to be close to or above the flow rate that you need to deliver that volume over 6 hours in the evening time. So now that we've determined our operating conditions for our pump system, we can put that value in here. We can put the head at operating conditions, the pump efficiency at operating conditions, which is estimated from this table, right? So the efficiency of a single pump operating at that flow rate is going to be the efficiency of the overall system, because each pump will be pumping a certain discharge, that discharge. And then we can then calculate the total flow rate, total head, and total number of pumps. And note that each of these yellow cells requires you to document the calculation in your write-up. The red cells are just single values that you put in, or constants. Now the second part, or kind of the middle part of this, once you figure out the operating conditions, this is obviously the hardest part right here. The middle part is then, okay, what's it going to cost to run these pumps? And so we're running these pumps for 6 hours, but note that we're going to be pumping different volumes in the summer than in the winter time. So we're going to basically add the number of days we have in the wintertime, and we describe that, we define that in this document. I think we say there's 5 months in the wintertime, or sorry, 5 months in the summertime, and then the wintertime would be the 7 months that are not summer. And so we're going to say, okay, what's the maximum volume? That would be the maximum daily demand in wintertime, maximum daily demand in summertime. And so we'll just be pumping those volumes over 6 hours. So we're going to have a different power consumption associated with that. And so you just kind of work your way through this, the pumping duration, the power output in foot-pounds per second, power output in kilowatts, and then using our efficiency value for the single pump that we calculated under the operating conditions of the single pump, we can then calculate the power input required. So if we go back to our pump curve, we get our efficiency value by kind of interpolating where we are in the operating conditions for a single pump, get that efficiency value, and then we can back calculate the power input based on the power output and the efficiency value. So then we get the total power input for all pumps. That's first for a single pump and then all the pumps operating. We get daily energy required for pumping in the summer and then pumping in the winter, length of summer, length of winter in terms of days, and then we can multiply the daily winter and daily summer energy inputs by the number of days. Ultimately, we end up with the annual energy cost. And we should give you a energy cost that's 6 cents per kilowatt hour. So annual energy cost for operating these pumps. And then finally, there's going to be a couple other costs that you'll calculate. So you will do pipe costs. And so that'll be the number of pipes that we have of a certain length, the unit cost per pipe, and then the total cost associated with that. And that is given down here in this table. So we have all the unit costs for each pipe. And so you can figure out how much the system costs based on the number of length of pipe and diameter of the pipe. Okay, so for the final table, we have the total pipe cost from table 13. We have the power output for the single pipes, or sorry, single pumps, total number of pumps. We have the cost of pumps and pump station, and that is going to be based off of this equation right here. So that equation gives us the total cost of pumps, where N is the number of pumps. This is our power output. This is our flow rate. So this equation relates all these variables to the total cost of the pump and pump station. So that's a capital cost. We've got the volume of our storage tank, elevation of the storage tank, and then cost of the storage tank. And that cost of the tank is based off of this. So each cubic foot of storage costs $6, and each foot of tank elevation costs $16,000. So you can imagine you want to optimize your system by minimizing that tank height, because that's a pretty big cost right there. So we'll plug those values in that equation to calculate the tank cost, our annual energy costs from table 12, annual energy costs, our project life cycle in years, we're saying that's a 30-year life cycle, and we've got a discount rate we're going to assume of 6%. So now we want to calculate the net present value factor, which is based off of this table. So I will let you figure out which discount factor you should use for net present value. And then you can actually calculate the net present value of the energy costs and then the total cost of the project. So ultimately, you'll end up with the total life cycle and net present value costs of the project. So those are that's an overview of the calculations that you'll do for this project. A lot of parts to it. In the deliverable, please include a write-up in which you document all the calculations that we've highlighted here in yellow squares, and a narrative kind of walking the reader through your calculations as well, so that someone who reads this report can follow the work you've done and recreate those steps. So you'll turn in the tables, you'll turn in graphs, and you'll turn in a discussion of your results as well as the sample calculations that are asked for. All right, that's it, and we can talk about it more in class and in office hours. Thanks.